Hi, my name is Shirag Shemmassian, and I'm an MCAT tutor at Shemmassian Academic Consulting. Thank you so much for joining me today. I'll be walking through an orgo passage. So typically this should take you about 9 minutes, but I'll be walking and talking through how I did it, so it'll be taking a little bit longer. But thanks again for watching, and let's get started. All right, so first I want to explain this blue background that I have in the back. I have it there because the number one important thing when you're doing your MCAT practice is to simulate test conditions. It's there because whenever we're practicing, we want to remember that we are supposed to be in the zone. So whatever you need to do to get in that zone, whether it's like go to a quiet place, go to your library, tell whoever you're living with to be quiet, whatever it is, you need to get in that MCAT zone. And so when you go in on test day, it's going to be exactly like how you practiced it, and it's just going to be that much easier to jump right into the exam with no distractions. So that's always my number one tip, and that's why I have this background, so we remind ourselves to get in that zone. Okay, great. So now jumping into the passage, the way I'll be doing it is I'll be reading through the passage, I'll be highlighting things that seem important to me, explaining my thought process throughout, how I get through this passage. And then we can get into the questions then. Okay, great. So let's start right off. Well, you can see that. Maybe I'll zoom in this way. All right, great. All right, so fluorine 18 radiolabeling typically includes several conserved steps, which includes elution of 18 fluorine from an anion exchange cartridge with a basic solution of potassium bicarbonate, this is potassium carbonate, and then potassium bicarbonate, and then cryptofix 2.2.2, and a mixture of acetonitrile and water, followed by rigorous azeotropic drying to remove the water. Okay. Researchers attempted to develop a non-anhydrous and minimally basic NAM technique to simplify the process and avoid basic conditions that can limit the scope and efficiency of 18 fluoride incorporation chemistry. All right, so what a jam-packed first paragraph right there. But right off the bat, these orgo passages especially can seem very daunting, can seem very confusing. It can definitely take the hang of it to really understand what the study that they're talking about is kind of focused on. But again, right off the bat here, I'm thinking about fluorine. I'm thinking about the properties that fluorine has. It's known for being basic. It is very electronegative. So I'm going to be thinking about that. And they talked about how it's in a mixture of acetonitrile and water. So I'm thinking about, okay, what is acetonitrile? It looks kind of like that. And water, we know, has 2 hydrogen ions. It can do hydrogen bonding. It has a very electronegative oxygen in the middle. And so these are just things that I'm drawing it out here, but necessarily on the exam, I maybe wouldn't draw that out just to save time, but it's also things that I'm thinking of, I'm taking note of. So it seems like basicity is like a really important factor here. They want to avoid that because that can get in the way of the efficiency of this experiment. So I'll just kind of keep that in mind, that they're not the most interested, I guess, in incorporating basicity into this experiment. But as of right now, I don't necessarily know what it's about. I just feel like fluorine is going to be a major player here, and maybe something to do with basic properties of solutions and molecules. But let's keep reading. Okay, let me do this. In a novel approach, researchers eluted 18 fluorine from small anion exchange cartridges. So there's that word again. We saw it back here, so I'll keep that in mind. Anion exchange cartridges with solutions of tetraethylammonium bicarbonate, perchlorate, or tosylate in polar aprotic solvents containing 10 to 50% water. After dilution with additional aprotic solvent, these solutions were used directly in nucleophilic aromatic and aliphatic 18F fluorination reactions, which prevents the need for azeotropic drying. So this just seems like a summary of what the study did. Seems to be a lot of kind of describing the methods. I'm not going to think too much into it at this point, just because sometimes the MCAT loves to do this on their science passages, especially on Orgo passages, where they'll tell you all these really nuanced information and details about the study, and you get to the questions and they don't ask you anything about that. So if you get stuck on this and you really try to figure it out and you spend 10 minutes just trying to understand what this one paragraph is saying, you get to the questions, you find that they don't even ask about it, big waste of your time, right? And we don't like to waste time on the MCAT. So again, just some things I've highlighted, things that we've seen before. We've seen these anion exchange cartridges before, polar aprotic solvents. I'm thinking about, okay, what that means. Aprotic, which means there's probably no hydrogen on it. Polar, okay, so it's not nonpolar. It has some sort of dipole quality to it. And then nucleophilic aromatic. Okay, so I'm thinking about nucleophilic aromatic substitution reactions. Just some things that I'm, again, just thinking about just so I can get to those ideas and those concepts quickly if I need to in the questions. But let's keep going for now. All right, so as proof of principle, NAM chemistry was utilized for the synthesis of the dopamine D2-D3 antagonist, 18F-phthalate. The standard synthesis of 18F-phthalate is known to be base sensitive. So again, there's that concept of, I'm going to highlight that because we talked about how earlier basicity probably wasn't the best for this. So they're saying that, again, here's a reaction that is base sensitive. Okay. Because of the tendency of the tosylphthalate precursor 6 to undergo hydrolysis and elimination side reactions, making this compound a good candidate with which to evaluate this minimally basic synthesis. Okay, so again, minimally basic looks like there's, some aspect of this molecule that undergoes hydrolysis and elimination side reactions. So I think we've gotten to the conclusion that we're going to be exploring more on this tosylphthalate precursor 6 and learning more about that. So now we go on to the figure. And I always like to read the figure captions first, just so I can kind of ground myself. And so it says NAM chemistry synthesis of phthalate. All right, so we are going to be looking at the synthesis of phthalate. Looking on this side, we have TEAP or T18F fluorine. Okay, so this I think we read that earlier with tetraethyl ammonium. Okay. So here's again this molecule you saw earlier, acetonitrile with water. So that's back here. So I'm not really, if you had me at this point explain back to you what this study is doing, I probably couldn't tell you, but I'm trying to make connections so I can tie it all together, just recognize molecules from earlier. And I think that really helps me, especially with Orgo passages, when, again, things can get very nuanced, very detailed, very complicated. Not even aiming for 100% comprehension, but just familiarity and, the confidence to be able to understand just at least the gist of the passage and see how everything connects together. I think that can really do wonders on an Orgo passage that could potentially very much overwhelm you. Okay, and so this looks like the molecule tosylphthalate, and they put it in this acetonitrile. Okay, so at this point in Orgo, synthesis, things like this, I'm really just going to be looking for major changes between probably it looks like this molecule and this molecule are very similar. So looking for major changes, the oxygens are the same. Looks like this amide group is the same. This amine is the same. The only thing that really changed here is this tosylate to a fluorine. So I'm going to highlight that. Just highlight that and keep that in mind. Okay, so that's the whole passage. Let me skim the description. I always skim the description. Sometimes you can find really helpful information in there, so I just like to give it a quick read. Okay, authors, non-anhydrous, minimally basic. So it's minimally basic again. For the simplification of nucleophilic 18F fluorination. So maybe this is a nucleophilic reaction. All right, and the rest is just formalities. Okay, Good. So we got through the passage. Again, at this point, especially on the MCAT, when things are very high pressure, there's a lot of time constraints, you're stressed out a little bit. Definitely probably could not explain to you perfectly what this passage is asking me, but that's okay. Let's go on to the questions and see what we can answer. All right, so question 1. In a novel experiment, researchers find a new 18F fluoride that can carry out NAM chemistry upon electron capture. Okay, which of the following best describes the element after positron emission? Okay, so classic example where the first question they ask you has basically nothing to do with the actual passage, right? You don't need to have read the passage to be able to answer this question. They're just asking you, if you have this initial molecule 18F fluoride and it undergoes electron capture, what would the element be like after this stated positron emission? So for this, we're going to be looking at beta decay. So that's when the molecule is shooting off a beta particle that's either a positron or an electron. And so this keeps the mass number of this element the same. It's going to keep the same mass number, but since the neutron turns into the proton, we're going to have a different number of neutrons and protons individually than we did before, because mass number, as just to refresh our memory, is neutron plus proton. That's mass number. But now we're going to have difference in the individual components. And so in positron emission, specifically electron capture, I like to think of it as like the molecule as a whole is getting more negative. It's losing positive. It's emitting a positive charge. So that's how I remember that. In this case, we're probably actually going to have there be another neutron as opposed to another proton. So in this case, we can use this formula. We start off with 18 fluoride and 9, because fluoride is the 9th element. So it's going to have 9 protons. And what happens is that it's not gaining any mass, but it is releasing this positron, which is a positive charge. So this is going to be our beta particle that shoots off. It's a positive charge. And so whatever this element is here must retain 18 at the top, and the denominators on this side need to add up to be 9. So what plus 1 equals 9? That's going to be 9 minus 1, which is 8. And on our periodic table, if we look at what is the element that has 8 protons, what is the 8th element? That is oxygen. So the answer to this question is going to be oxygen with a mass number of 18. It has 8 protons and 10 neutrons, because from the original fluorine, one of its protons actually turned into a neutron. That is positron emission. So this would be the opposite. That would be probably electron emission. All right, so looking at the answer choices here, we have C, 18O oxygen, which is going to be our answer. All right, let's keep going. Researchers discover that high concentrations of a protic solvent in a new experiment, I'm going to highlight that, prevent nucleophilic aromatic 18F fluorination reactions necessary for product formation. Which of the following best explains this observation? Okay, so I'm thinking about a couple different things here. I'm thinking about what is a protic solvent. Protic solvents are, in the name, even if you had not background knowledge on this. Protic sounds like proton. What are protons in chemistry? Usually hydrogen atoms. So it seems like protic solvents are probably going to be more positive inclined. They have hydrogen atoms in them. So that probably means with hydrogen atoms that they can do hydrogen bonding. So if they're getting in the way of nucleophilic aromatic reactions, that means that knowing what we know about nucleophilic molecules, they're usually molecules that are having a large negative charge or electron density. So they're probably this positive charge, positive, molecule of the protic solvents are probably bonding with the negative charge of the nucleophile, and kind of neutralizing that reaction. So let's go into the answer choices here. We've kind of deduced that the proton is probably going to be bonding with the nucleophile, or the negative aspect of that nucleophile. So let's see, protic solvents will hydrogen bond with nucleophiles, thereby decreasing nucleophilicity. That sounds pretty on the dot with what we were talking about, but let's keep reading. Let's read the other answer choices before we get to a conclusion. All right, B, protic solvents will hydrogen bond with electrophiles, thereby decreasing electrophilicity. So this question doesn't actually mention electrophiles, doesn't really talk about any interaction between protic solvents and electrophiles, and considering what we know about electrophiles, that they're more positively inclined, and what we've deduced about protic solvents, that they probably have a lot of positive hydrogens, doesn't really seem like positive would bond with positive. So this doesn't seem plausible. We can cross that out. All right, protic solvents will form van der Waals interactions with aromatic rings, thereby decreasing nucleophilicity. So again, given that protic solvents probably have a high concentration of hydrogen ions, doesn't seem like nucleophilicity would be influenced by any van der Waals interactions. Doesn't seem like these hydrogen ions will be very keen in forming these non-polar interactions, so that's probably not the answer. Protic solvent will form dipole-dipole interactions with electrophiles, thereby decreasing electrophilicity. So again, like we mentioned earlier, electrophiles are generally more positive. Protic solvents are also generally more positive, so there's no huge dipole there being formed. And then also this is not, concerned with the electrophilicity, so it doesn't seem like the right answer either, which leads us back to answer A. And we had a hunch that was probably our answer, but always good to check, always good to make sure that we're not ruling anything out prematurely. All right, let's go to question 3 now. Which of the following functional groups present in compound 6 is important for the hydrolysis side reaction? A, ether, B, ester, C, amide, D, amine. All right, so for a question like this, knowing your functional groups obviously is key. That is actually one of the first things that I memorized when I was studying for the MCAT, that and amino acids, which actually they go really hand in hand. And they're very, they pop up in the biochem section all the time, orgo section, chem phys. So definitely really great thing to start off with doing, and helps you build that foundation. But all right, so a great way to kind of do this quickly is to know your functional groups and know what they look like. So if we look at an ether, we know that an ether is an R group bonded to an O bonded to an R group. So that's an ether. An ester is going to be a carbonyl O bonded to an oxygen bonded to an R group. An amide is again going to be a carbonyl O bonded to a nitrogen, with any number of R groups. And then an amine is just going to be a nitrogen bonded to R groups or hydrogens if the R is a hydrogen, up to 3. And so again, up to, so then this would be up to 2. Okay, so let's go through compound 6 here. And always good to refer to the figure. We don't want to guess. It's right there. We can definitely look at it. And so let's see if we have any of these groups here. All right, so ether, ROR. Looks like we do have an ROR right here. Ester is a carbonyl O bonded to an O and an R. So we have only one carbonyl O here, but on both sides it's actually bonded to a carbon on this side and a nitrogen on this side. So that doesn't make it an ester, but that does mean it is an amide. So it looks like we do have an amide, and an amine, which is a nitrogen bonded to R groups. Looks like we have that too. So right off the bat, that was helpful because we now can cross out B since that's actually not even in the molecule. So we can cross out B. Now we need to figure out which one of these 3 remaining functional groups is important for the hydrolysis side reaction. And so if we go back into the passage, we can find that the hydrolysis side reaction is probably the standard synthesis of 18-phthalate is going to be base sensitive because of the tendency of the tosyl-phthalate precursor 6 to undergo hydrolysis and elimination side reactions, making this compound a good compound with which to evaluate this minimally basic synthesis. So we probably are looking for something that is relatively reactive. If it's going through side reactions all on its own, it is generally going to be a more reactive compound that is undergoing this reaction. So if we look between our options, ether, amide, amine, we can probably instantly cross out this amine since it's a nitrogen bonded to 3 R groups. It's not very reactive. There's a lot of steric hindrance. This is not a molecule that's very likely going to just undergo a side reaction. And amines in general, something good to know about them is that they're just not very reactive molecules. So we can cross out amine. And so now let's look at ether and amide. I really want to hone into this amide because it has this carbonyl. In the Orgo passage, anytime they're asking you about reactivity, molecules with carbonyls are always going to be one of the more on the more reactive side. Okay, they have this very strong partial dipole here with the carbonyl carbon and the carbonyl oxygen. And so generally it's just going to have a lot of resonance and the electrons are going to want to move around. But they're probably going to be on the more reactive side. And so between an ether and an amide is definitely more reactive. I mean, this ether is bonded to 2 R groups. Again, there's kind of that aspect of steric hindrance. There's not really a big inclination for these electrons to move on either side. So the way that this dipole is probably set up is relatively even. It kind of evens out on both sides. And so the ether is not very reactive, but the amide with this partial dipole here is very reactive. And so in this case, between an ether and an amide, definitely going to choose an amide to be the compound or the functional group that's most going to undergo that hydrolysis side reaction. All right, so let's go on to question 4 now. Okay, researchers are having trouble obtaining pure compound 6. They hypothesize that protonating the amide nitrogen compound 6 will allow them to use which of the following columns for purification. All right, so right before I go to the answer choices, I'm actually going to go figure out what does protonating the amide nitrogen in compound 6 do. So let's go to the compound here. We can always refer back. I definitely don't have it memorized. And it looks like we're going to be looking specifically at the amide nitrogen. So we're going to be zooming into that. I'll just redraw that here. So we have the carbonyl, we have the nitrogen bonded to a hydrogen and an R group. And so right now this nitrogen has a formal charge of 0. And formal charge again is calculated by taking the number of valence electrons. So nitrogen has 5 valence electrons minus, I like to just count the number of bond lines. So if it's a double bond, I would count it as 2. And so this has 3 single bonds around it, so minus 3, minus the number of electrons that are around it, which is 2. So 5 minus 3 minus 2 is 0. So it has a formal charge of 0. If we were to protonate the nitrogen, we would do the oxygen, we'd have the nitrogen, has an R group, has a hydrogen. Now it has another hydrogen and no lone pair electrons around it. So now this nitrogen has a formal charge of +1. And you can kind of practice how to get to that +1 number given the framework that we did here. But all right, so it has a formal charge of +1, giving it a positive charge and giving the overall compound 6 a positive positive charge. So now it's acting more like a cation. Okay, with that in mind, let's go back to the question. So the question's asking, how can we get this positive compound in its most pure form eluted out? And so the question says the answer choices say A, anion exchange, because the positive charge on 6 will bind the negatively charged resin. All right, so all things set aside, the answer does get it right. It says that 6 has a positive charge. But if we look at B, it says that 6 has a negative charge. And same with D, it says that 6 has a negative charge. And we just confirmed that protonating the amide nitrogen would give this nitrogen a formal charge of +1, giving it a positive charge, giving the overall compound 6 a positive charge, because nowhere else in compound 6 is there a negative charge to cancel out this positive charge. It is overall net positive charge. So right off the bat there, we can cross out B and D because it states that 6 is going to have a negative charge. So now we're between A and C. It says the only difference here is whether it's an anion exchange column or a cation exchange column. And so when learning about purification, you'll learn that these two specific columns are named for the type of molecule it is trying to elute out. And so now that we know that compound 6 is a cation, we know that we're probably going to want to use a cation exchange column. And how does a cation exchange column actually work? So you put in, whatever compound that's a mixture of positive and negative charges, and you want to capture your cation. So you are basically going to be flushing out the negative charge. You want to capture the cation in the resin. And so if you want to capture the cation in the resin, inside the actual column, you're going to need molecules that attract cations, which are just going to be negatively charged resin molecules. And so on the inside, we're going to have negatively charged resin for these positive cations to get stuck to so they don't elute out. So that would make C the right answer, cation exchange, because the positive charge on 6 will bind the negatively charged resin. So C is going to be our answer. All right, and that's this passage. I hope this helped and gave you guys some strategies on trying to figure your way through the Orgo questions on the MCAT. They are limited, but they're still important. You want to get all the points you can. So again, thank you guys so much for watching. I hope it helped. Definitely be sure to check out our other videos. We have a lot of passage walkthroughs and 528 study strategies. And yeah, we just really appreciate you guys watching. So thanks so much. Best of luck and bye.